Hello friends, I welcome you in lecture number 7 on heat equation. In previous lecture we have discussed that how to obtain the solution of heat equation in which the boundary conditions are given that temperature gradient is 0 at both the endpoints. That is how to obtain the solution of heat equation if we have this type of boundary conditions. If it is given that ends of the bar are insulated, then we know that temperature gradient, that is del U by del X, is 0 at all those values of X which lies between 0 and L. So we have seen in earlier lecture that the solution of heat equation with this type of boundary conditions and this initial condition is given by uxt equal to sigma an cos n pi x over L e raised to minus lambda n square times t, where lambda n is given by c n pi over L, a0 is given by 1 by L integral 0 to L of function fx, and an is given by 2 divided by L integral of fx multiplied with cos n pi x over L with respect to x from 0 to L. And we will apply this formula if it is specified that our metal bar is in such a way that both the ends of the bar are insulated. So here we are going to discuss one question in which we are going to use this formula, or we are going to consider the metal bar in which both the ends are insulated, and this question was asked in GTU Winter 2019 exam. Question is, find the temperature in the thin metal rod of length L with both the ends insulated and initial temperature is sin pi x divided by L. So here they have specified that both the ends of the metal bar are insulated. That means we have boundary conditions are del U by del X is 0 at both the ends. Here bar is of length small l, so here we write del U by del X at L comma T. So we have this type of boundary conditions. Initial temperature is given by this function fx, which is sin pi x divided by L, and here we will apply this formula and we will be able to decide this a0 an lambda n, and then we will substitute them into this equation. So we know that whenever we are interested in the measure of temperature in the thin metal rod at any point x and t, then this problem is governed by heat equation, which is del U by del T equal to c square times del square U by del x square. The solution of this heat equation together with these two boundary conditions and one initial condition is nothing but temperature distribution in the thin metal rod of given length. So here first we start by writing that the heat conduction is governed by this equation, which is heat equation, and it is given that both the ends of the bar are insulated. Both the ends of the metal rod are insulated. Therefore boundary conditions are del U by del X at small x equal to 0 for all time t, and del U by del X at small l equal to 0 for all values of t. So this is true for all values of t greater than or equal to 0, and they have given that initial condition is U at t equal to 0 is sin pi x divided by L, and this is for all values of x between 0 and small l. Here length of the metal rod is small l, so we will use small l. So first we write down what is we find out that A0 and An first. We have the formula for the solution. We are going to use this formula, and for this formula we will require all this lambda n, A0 and An, where fx is given by initial condition. So we will first obtain A0 and An, and that is simple integration. So here we can say that this is our small fx, and first we find out A0, which is given by 1 divided by L integral from 0 to L fx dx. Here length is given by small l, so we are using small l instead of capital L. 0 to L fx is sin pi x divided by L integral with respect to x. Integral of sine function is minus cosine function, so here I am writing minus cosine of pi x divided by L, and I have to divide by coefficient of L. So in the division I will write pi divided by L, or that I can write in the numerator as L over pi, and limits of x are from 0 to L. Upper limit is x equal to L, and before that we can cancel out this L. We can take this minus L over pi outside. L will get cancelled because they are independent of x. We can take them outside, and then we can take limits of x as 0 and L. If I take x equal to L for upper limit, then this is going to be cosine of pi. If I take x equal to L, that will cancel this L. So for upper limit I have cosine of pi, minus for x equal to 0 I will have cosine of 0. Now cosine of pi is nothing but minus 1, and cos 0 is 1. So this is minus 1 by pi times minus 2, and therefore we have 2 divided by pi. This is the value of A0. A0 turns out to be 2 divided by pi. Similarly, we have to obtain value of An. So we have again ready-made formula for An. An is 2 divided by L integral from 0 to L fx multiplied with cosine of n pi x over L integral with respect to x. Instead of capital L, we have small l as the length of the metal rod. Fx is sin pi x divided by L, and this is cosine of n pi x divided by L. And to integrate this, we can use that formula that we can take these 2 inside, and let me write this first. 2 cosine n pi x divided by L into sine of pi x divided by L integral with respect to x. Now I can use that formula that if I have 2 cos alpha into sine beta, that is 2 cs, is nothing but 2 cs is s minus s. We can use this formula. So using this formula, this is like 2 cos alpha into sine beta equal to sine of alpha plus beta minus sine of alpha minus beta. Here we can consider alpha equal to n pi x over L and beta equal to pi x over L. So first we use this formula and we rewrite in this form. 2 cs means sine of alpha plus beta. Alpha is n pi x by L plus pi x by L. So we can see we have pi x by L common. So we can write in this way: n pi x plus pi x common, and in the denominator we have L. Similarly, sine of n pi x minus pi x, that is n minus 1 pi x divided by L. Integral is from 0 to L with respect to x. Now we integrate this. Integral of sine function is minus cosine function, this 1 by L as it is. Integral of sine is minus cosine of n plus 1 pi x divided by L, and I have to divide by coefficient of x, which is n plus 1 pi divided by L, that I can write as L divided by n plus 1 times pi. Same thing here, integral of sine is minus cosine, and due to this negative sign we will write plus, and here also coefficient will be n minus 1 pi divided by L, and if we write in the numerator we can rewrite it as L divided by n minus 1 into pi cosine of n minus 1 pi x divided by L. Limits are from 0 to L. Now if we take x equal to L as upper limit, here L will get cancelled and we will have cosine of n plus 1 pi. Same thing here, plus cosine of n minus 1 into pi. And before that we can see that here we can cancel out this L, and we can take minus 1 over pi or 1 over pi outside this. So we can do it simultaneously. L will get cancelled, and we can write 1 over pi outside, and if we take upper limit, for upper limit we will have cosine of n plus 1 times pi if I take x equal to L, and in the division here I have n plus 1 into pi I have written outside, and here don't forget to write down negative sign. L will get cancelled. Same thing here if I take x equal to L will get cancelled, and I am left with cosine of n minus 1 times pi divided by n minus 1. This is for x equal to L. For x equal to 0, we will have cosine of 0, that is 1, and we will have minus 1 over n plus 1 here, and same thing here we will have 1 over n minus 1. So for upper limit we have minus 1 divided by n plus 1 plus 1 divided by n minus 1. This pi we have taken outside this. And here we can observe one more thing, that we have n minus 1 in the denominator. So this is valid if n is different from 1. So we have to calculate, for n equal to 1 we have to calculate an separately. Now let me simplify this. This is 1 over pi. This cosine of n plus 1 into pi, that is going to be minus 1 raised to n plus 1 divided by n plus 1. Same thing here we have minus 1 raised to n minus 1 divided by n minus 1, and if I take this negative sign inside this bracket, I will have 1 over n plus 1 minus 1 over n minus 1, and of course this is valid for all n different from 1. Now we try to rewrite all these things. We can rewrite minus 1 raised to n plus 1 as minus 1 raised to n into minus 1 divided by n plus 1. Same thing here, minus 1 raised to n times minus 1 raised to minus 1 divided by n minus 1 plus 1 over n plus 1 minus 1 over n minus 1. Again this is valid if n is not equal to 1. Now let me simplify again. This is 1 over pi. Here minus 1 into this minus 1, that is going to be positive, and we have minus 1 raised to n divided by n plus 1. Here this minus 1 raised to minus 1 is going to be minus 1. So here I have negative sign, and minus 1 raised to n divided by n minus 1 plus 1 over n plus 1 minus 1 over n minus 1. And of course I have to write this is valid if n is not equal to 1. Now this becomes 1 over pi. Here now I can take this minus 1 raised to n common, and in the bracket I can write 1 over n plus 1 minus 1 over n minus 1, and these two also I can write in the bracket. So 1 times 1 over 1 plus 1 n plus 1 1 over n minus 1, n is not equal to 1. And now we can see again this is common, and if we take this common we will have minus 1 raised to n plus 1. So that is now 1 over pi minus 1 raised to n plus 1 into 1 divided by n plus 1 minus 1 divided by n minus 1, n is not equal to 1. And let's simplify this again. This things as it is, minus 1 raised to n plus 1. Here we have in the denominator LCM is n minus 1 times n plus 1. Here we will have n minus 1 minus n plus 1. N is different from 1. Now we can see n will get cancelled, and here we will have minus 2, and this is going to be n square minus 1. So finally in the denominator I have n square minus 1, and this pi. In the numerator this is going to be minus 2, and this minus 1 raised to n plus 1. N is not equal to 1. So finally we find that a suffix n becomes minus 2 divided by n square minus 1 times pi into minus 1 raised to n plus 1. N starts from 2, 3, 4 and so on. This is our an, but this is valid for n starting from 2, and we are not having any information for n equal to 1. So we have to obtain value of an for n equal to 1 separately. So here I am writing, now I am trying for finding a suffix 1, that is an for n equal to 1. So we can start from the very first step, or we can put n equal to 1 here, and we can start from this. Suppose I give this number star, then I will take n equal to 1 in star, and I will have a1 equal to 1 by L integral 0 to L 2 cos pi x by L sin pi x by L. So now I am taking n equal to 1 in that equation. So I am writing here, taking n equal to 1 in equation number star. We have a1 equal to 2 by L. 2 I think we have taken inside, so here I have to write 1 by L, and 2 cosine of n by x by L. N is 1, so I have cos pi x by L times sin pi x by L integral with respect to x. Now this is famous identity, 2 sin theta into cos theta can be written as sin of 2 times theta. So here this I can replace by sin of 2 times pi x by L, that is 2 pi x by L, using the formula that sin 2x is 2 sin x into cos x. And now this is simple integral. Integral of sine function is minus cosine of 2 pi x divided by L. In the division I have to write 2 pi over L, that I can rewrite as L divided by 2 pi limits of x are from 0 to L. Now I can rewrite this by cancelling this L. So let me rewrite this as minus 1 over 2 pi. L will get cancelled. Cosine of 2 pi x by L. Limits of x are from 0 to L. So this now I can rewrite as minus 1 over 2 pi. For x equal to L, this becomes cosine of 2 pi, and for x equal to 0, it is cos 0. Cosine of 2 pi is 1 and cos 0 is also 1. That is 1 minus 1 is 0. So we find that value of a1 is 0. And from n equal to 2 and so on, we have this formula for an. Minus 2 divided by n square minus 1 pi minus 1 raised to n plus 1. And we have to write lambda n also. What is lambda n? It is given by Cn pi divided by L. And here n takes the values. Here I have to write n from 0, 0, 1, 2, 3 and so on. Because here we have lambda 0 also, that is 0. And once now we have written all these things, we have obtained a0, an and lambda n. So we can write down the required temperature. What we are asked to find out? We have to find out the temperature in a thin metal rod. Find the temperature in the thin metal rod of length L. So temperature at any point x comma t. So that we have to write now. So once we obtain all these things, we have to just put them in that formula. So therefore the temperature in a rod is uxt. This is given by sigma n equal to 0 to infinity an times cosine of n pi x by L e raised to minus lambda n square times t. Now here a0 is different, so let me write this as, first we write the term corresponding to n equal to 0. For n equal to 0, we have a0, cosine of n is 0, that is cos 0 is 1, e raised to 0 is also 1. For n equal to 0, here I will have lambda 0, and lambda 0 is 0. And plus sigma n equal to 1 to infinity an cosine of n pi x by L e raised to minus, now lambda n we have obtained, it is Cn pi divided by L. So we will take square of it into t. Now what is a0? a0 we have obtained separately. I think it is 2 divided by pi. So we will write a0. First we have to write a0, then an. So let me write a0 here. It is 2 divided by pi. And a1 we have obtained separately, but a1 is 0. So here instead of writing from n equal to 1 to infinity, I will write n is from 2 to infinity. And value of an is minus 2 divided by n square minus 1 into pi into minus 1 raised to n plus 1. This is what we have obtained for an. Cosine of n pi x divided by L e raised to, this I can rewrite as minus c square n square pi square t divided by L square. Let me check value of an again. Minus 2 divided by n square minus 1 pi into minus 1 raised to n plus 1. That I have written here. Now if you observe this minus 1 raised to n plus 1, is 0 if n is odd. If n is odd, then minus 1 raised to n will become minus 1, and we have plus 1, so this is going to be 0. So these values of an are 0 if n is odd, and if n is even, minus 1 raised to n is 1, and I will have 1 plus 1, that is 2. If n is even, then value of this bracket is 2. So we will have non-zero contribution for even values of n only. For odd values of n, we have an equal to 0. So now we are writing for even values only. So let me rewrite this as 2 divided by pi. Here I can write this as sigma n equal to, instead of writing 2 to infinity, we can write 2, then 4, then 6, and so on. This is continue for even positive integers. If n is even, then this bracket minus 1 raised to n plus 1, that is going to be 2. So I am writing 2 there. Here I will have n square minus 1 into pi, and these things as it is, cosine of n pi x by l e raised to minus c square n square pi square t divided by l square. If we wish, we can rewrite this in another form also, because n is even here. In this part n is even, and n takes the values 2, 4, 6 and so on. So we can replace n by 2m, where m is positive integer. So we can rewrite in another way by taking n equal to 2m, and value of m will start from 1 to 3 and so on. And simultaneously we can observe that this is minus 4 and divided by pi. So that quantity is independent of n, so that we can write outside summation minus 4 divided by pi. Here we will write sigma from m equal to 1 to infinity, and we will take n equal to 2m everywhere in this formula. So I have n square, and if I take n equal to 2m, I will have 4 into m square minus 1, and I have taken this pi outside, so I am writing only 1 divided by 4 into m square minus 1. Here I will write n equal to 2m, so cos 2m pi x divided by l, and into e to the power minus, here also I will have n equal to 2m, and square of 2m is 4m square. So this m square n square is replaced by 4m square. So I am writing 4c square m square pi square t divided by l square. M takes the values from 1 to infinity. So either we write in this form or in this form, both are valid. We are rewriting this by changing the summation index. Instead of writing n equal to 2, 4, 6 and so on, I am taking n equal to 2m, where m can take any positive integer, and I have put n equal to 2m everywhere in this formula, and I obtain this expression for the temperature in a thin metal rod at any time t and at any position x. So in this way we can easily solve this type of problems, and they are asking this type of problems in GTU exams. This question was also asked in GTU Winter 2019 exam. All I have to remember is that if it is specified that we have metal rod with insulated ends, then we have these boundary conditions, and if we have this type of boundary conditions, then the formula is containing cosine terms. Here we have this difference, cos n pi x over l. In earlier case, when both the ends are kept at 0 temperature, the formula was sigma bn sin n pi x by l into e raised to minus lambda n square t. Now instead of sine function we have cosine function, that is the only difference. And here we have to obtain Bn for n equal to 1 to 3 and so on. Here n starts from 1 to infinity, here n starts from 0 to infinity, and we have to obtain a0 and an using these two formulas. Rest of the things are as it is, but we have to remember that if we have this type of boundary conditions, we have to use this formula which contains cosine terms, and this formula we will use if we have this type of boundary condition, that is temperature is 0 at both the ends, and here temperature gradient is 0 at both the ends, or both the ends are insulated. So in this way we can easily answer this type of questions, and we will continue with more problems of this type in upcoming lectures. Thanks for watching.